This is the differential amplifier we started analyzing. We showed last time that this circuit with the two MOSFETs and the two resistors and the current source in the middle rejects common inputs when the two inputs are equal. We don't see any output, and amplifies differential inputs when there's a difference between the two inputs. The circuit amplifies the difference between these two inputs. And we also showed that when the two inputs are plus VID over 2 and minus VIT over 2, so fully differential, we call this fully differential, the signal voltage here at this node, the source of the two MOSFETs, there's no signal here, right here. So this voltage Vs would be zero, signal zero. So if this is a virtual ground, when the two inputs are differential, this here is virtual ground. Same here. So virtual ground, not a real ground, not hardwired to ground, just a virtual ground. No signal appears there when the two inputs are fully differential. And you consider this part of the circuit. I have a MOSFET with its source at a virtual ground, with an input at the gate, the output taken from the drain, and a resistor between the drain and the supply. If we look at this part of the circuit, I have the exact same thing. The circuit is symmetrical. So here I have also a MOSFET with input at gate, source is grounded, output taken from the drain, and the resistor RD between the drain and the supply. We call this half circuit. And same for this. And we will refer to them as half circuits. And we will use them actually to analyze differential amplifiers. The reason we will use the half circuits to analyze differential amplifiers is that if you look inside the half circuit, we have something that we're now very, very familiar with. And this is the simple common source amplifier. We've been studying this common source amplifier since EECE 310. So we're very, very familiar with it. And the half circuit is just that. When we have a virtual ground here, the half circuit is just Q1 with resistor RD, input at gate, source grounded, output at the drain. That's my very good friend, the common source amplifier. And this means that I can use all the knowledge I know about common source amplifiers and apply it here. And this is what we will do. We will try to, again, recycle things that we know and use formulas that we know to analyze new circuits. So the new circuit in this case is the differential amplifier. I don't want to come up with a set of formulas for differential amplifiers. I will just transform the differential amplifier into a common source amplifier, use the formulas that I know from common source to get what I need for differential amplifier. So this technique is called the half circuit concept. So when Vs is 0, no signal, when the two inputs are applied differentially, we see here the half circuit. So at the input here at the gate, I have VID over 2. The two inputs are applied differential. One of them is VID over 2. The other is minus VID over 2. This is the first output, VO1. And of course, the MOSFET is biased at I over 2. I is the current in the current source. So now I can apply the formulas of common source. I know for common source that, for example, the gain is minus GM R prime L. This is a well-known formula for common source. The gain is minus GM, in this case GM1, R prime L. R prime L is really not one resistor. It is whatever appears between the drain of the MOSFET and ground. And in this case, it will be RD to signal ground in parallel with RO of the MOSFET. So this will be RD parallel RO. So minus GM1 or just GM, RD parallel RO. And this will be the gain. So VO1 over VID over 2, because the input is VID over 2. And this gives me an equation which is exactly the same as the one we derived previously. So VO over VID over 2, and in this case, the output is VO1 at the first drain, is minus GMR prime L. So VO1 over VID is minus half GMRO parallel RD. That's a result that we got previously on the previous slide. You see it here. That's it. When we take the output from one drain, we call that single-ended. The output is plus or minus half GMRO parallel RD times VID. Why is it plus or minus? Because there is also VO2 that we're not showing. There's the other half circuit here that gives me VO2 from the drain of Q2. So VO2 would be the plus, VO1 is the minus. And if I take the output between the two drains, VO2 minus VO1, then I get GM times RO parallel RD. So that's a nice technique, and we will try to use it whenever we can. And in fact, let's see if we can apply it when the two inputs are equal, not fully differential. When the two inputs are equal, I call this the common mode. If I have common mode inputs, so they're equal, what should be the common mode gain? Well, if the two inputs are equal, the common mode gain should be 0. The circuit rejects common mode inputs. All right, let's see if this is true. This is my circuit, and now if you look at the two inputs, they're equal, and they're both equal to VICM, so the common mode. Now, I will also consider the current source to be non-ideal, because we will see that if it's ideal, then in all cases, the output will be 0. So what is RSS? RSS is not the resistor that's connected in parallel with I. RSS is actually the output resistance of the current source. But we're showing it here because what I want to do is I want to also apply the half circuit technique in this case. So I want to try to split the circuit into two half circuits. Okay, so this is the split here. And on the left, we have a half circuit, which is exactly the same as the one on the right. RD, RD, MOSFET, MOSFET, they're identical. And then we reach here where I have just one RSS. In the signal analysis, this becomes an open circuit, and I will have just RSS. How can I split RSS into two half circuits? What I can do is say, well, this RSS is like two RSSs, two RSSs in parallel. So this is like saying I have a two RSS here in parallel with two RSS here. If you take the parallel combination of two RSS and two RSS, you get RSS. And that's a convenient way to show RSS, because now on the left, I have two RSS, and on the right, I have two RSS. So now the half circuit in this case would be RD, Q1, two RSS between the source and ground. And the other half circuit on the right would be exactly the same. RD, Q2, and two RSS between the source of Q2 and ground. Now you may wonder why do we see the two RSS in this case, or the RSS, and we don't see it in the previous slide. The reason is the following. When I have common mode inputs, the signal here, what we call VS, would not be zero. But if I have fully differential inputs, VS would be zero. Remember the seesaw effect that we talked about? If these are equal, when this goes up with it. And VS goes up with them. And when this goes down, this is equal, it will go down with it, and VS will go down with them. If I have differential inputs, let me change the color for differential inputs. So blue would be differential inputs. If this is VID over 2, this would be minus VID over 2. So this is what happens. The blue colors is the situation when I have fully differential. And when this goes up by this amount and this goes down by the exact same amount, this would not move and it would be virtual ground. But if we go back to the red situation where the two inputs are equal, as they oscillate, as they dance together, VS dances with them. So I have a signal at the source when the two inputs are equal. And that's why I care about what's between this and ground. Now, two RSS and two RSS are important because they're between the node here and ground. Previously, when we had only differential, when we had the differential case, the blue, this VS was ground, and the RSS was between ground and ground. So it did not affect the circuit in any way, and I completely ignored it. Now I can't ignore it because there is a signal at the source. And here's the half circuit in this case. The two MOSFETs, each with its RD and its two RSS. The two inputs are equal to VICM. And the two MOSFETs are biased at I over 2, the current source current divided by 2. And again, if you look at the half circuit, we have something that we're familiar with. And that's, again, a circuit where I have a MOSFET with input at gate, output at drain, and RD between the drain and the supply. However, here the source is not grounded. There is a resistor, 2 RSS between the source and ground. And we know what this circuit is. This is a common source amplifier with a resistor between the source and ground. And that's something that we know, we've seen this, and we have a set of formulas for that. We know that the gain would be something like minus GM RD over 1 plus GM times the resistance between the source and ground. So that's a formula you can get from the formula sheet for the gain of this. When I neglect small RO. minus GMRD divided by 1 plus GM times the resistance between S and ground. If I have a small RO, then we also have a formula for that, so it won't affect our analysis. We can just look it up in the formula sheet. This is, after all, just a common source amplifier with a source resistor. So the gain is minus GMRD over 1 plus GM times the resistance between S and ground, which is equal to 2 times RSS. So that's the gain. Minus GMRD over 1 plus GM times 2 RSS. So that's 2 GM RSS. And this is at the first drain, and it's the exact same voltage at the second drain. So there is a bit of a contradiction here, because when we started this discussion about differential amplifier, we said that if the two inputs are equal, there is nothing that we will see at the output. But now this formula is telling me that there is something that we will see. So why are we getting a different result? The reason is that when we did the analysis, we assumed that the current source I is ideal. So its RSS will go to infinity. This would be infinite if the current source is ideal. And if RSS is infinite, what happens to this gain and the output? It will go to 0. If RSS is not infinite, if the current source is non-ideal, it will have a certain RSS, and we will see some output even if the two inputs are equal. So the circuit doesn't reject the common mode inputs completely, 100%. We may have some output, but typically this gain is very, very small. And I can get rid, even if the current source is non-ideal, I can still get rid of the output if I take the output differentially. Because if I take VO2 minus VO1, if I consider my output to be between the two drains, because the two drain voltages are equal, then I can get rid of the output completely, even if the current source is non-ideal. If I have to take the output single-endedly for some reason, then that's fine. I will have some output. So that's like the first non-ideality here. The non-ideal current source will cause an output to appear at the drain of each MOSFET. And the gain in this case is this ACM minus GMRD over 1 plus 2 GM RSS. And we can calculate the CMRR, which is 20 log base 10 of AD over ACM. So that's not really bad news, because usually RSS is very large, or I can make it very large. And if RSS is very large compared to RD, then GMRD over 1 plus 2 GM RSS can be made much less than 1. And therefore, the output would be a smaller version of the input when the two inputs are equal. So ACM can be, for example, 0.1 or minus 0.1. So minus 0.1, this means that when the two inputs are equal, they're equal to some VICM, the output would be minus 0.1 VICM. So we're not really amplifying, we're attenuating the common mode inputs, while the differential inputs would be amplified by maybe a factor of 20 or so. And this will give me a CMRR, which is 20 log AD over ACM, so 20 log 20 over 0.1. Okay, let's analyze now a differential amplifier built out of just MOSFETs. This is a CMOS, simple CMOS differential amplifier using NMOS transistors like M1, M2, and M5, and PMOS transistors like M3 and M4. So is this really a differential amplifier similar to the amplifiers or amplifier circuit we saw? And the amplifier circuits we saw, I had a resistor here and a resistor here and a current source here. Now, instead of the resistors, RD and RD, I have MOSFETs, and instead of the current source, I have another MOSFET. And the MOSFETs can, in fact, act as a resistor or a current source. So in the signal analysis, if I have a MOSFET like M3, as far as M1 is concerned, it's looking into the drain of M3, and there is a DC no signal here at the source of M3, and no signal, a DC voltage at the gate of M3. And we know that when we do that, when we look into the drain of a MOSFET with no signal at gate, no signal at source, we will see it's small RO. So M3 is presenting itself as a resistor, and the resistance of this resistor is small RO3, and the same can also be said about M4. So instead of using resistors, I can use MOSFETs, and they would behave as if the resistors as far as signals are concerned. To be able to do that, the sources have to be at some no signal voltage, and their gates have to be at some no signal voltage, so pure DC. And then I can use the rule and say that RD in this case is equal to RO3, and that should be equal to RO4. What about the current source? Can I use a MOSFET to build a current source? Yes, of course. We saw that. We saw that we can use MOSFETs to build current mirrors. So this is this may be the M5, maybe just mirroring something. So this may be coming from a circuit that I am not showing, something like this. So maybe there's a reference here, or it can be it can be simply a resistor here, and there is a MOSFET, and M5 is just mirroring this IRF to implement ISS. And we said previously that we don't always show this part because this is shared by maybe several circuits. So we don't show it, we just show that we have a V bias 2 here, the VGS of M5 and M6. What about V bias 1? How do you generate V bias 1? We know how to generate V bias 2. This is the way to do it. How do you generate V bias 1? Same thing, we can also use a P MOSFET here. And in fact, I can connect it to this node. And that can generate for me V bias 1. So this can go here. So using the reference current source, I mirror that to generate ISS, and also benefit from it to generate this V bias 1 that I need here. So that's how we can generate V bias 1 and V bias 2. And now What's the question? What's the voltage gain? Okay. What is the voltage gain? All right. The voltage gain is the output voltage divided by the input voltage. That's voltage gain. So let's see, where is the output? Here's the output. It's indicated on the schematic. On the circuit diagram, the output is taken from the drain of M2 to the drain of M1. The difference between the voltages at the two drains, that's considered my output. But what's my input? Well, this question is confusing because such amplifiers have two different kinds of gain. There is common mode gain and there is differential gain. So this question is not complete. I need to say here what is the maybe differential, and then I can answer it. Common mode, and then I can answer it. But the way it is written now, what is voltage gain? Okay, fine. I'll calculate the two. But do you want the differential? Do you want the common mode? So whenever you see a circuit like this, you have to specify where is the output and what kind of input do you have. Now on the schematic, we know where's the output. But if this V out was not indicated on the schematic, the question would be more confusing because what is the voltage gain? And we don't know where's the output and we don't know what is the type of input. No. Sa'ata, I will have to calculate the gain when the output is single-ended and the gain when the output is differential for the two cases of differential input and common mode input. So I have 4 cases or more. Luckily, we know that the output is here, so the output is determined. This is the output. I don't need to guess. Is this differential output or single-ended? It's differential. And I know where's the plus and where's the minus. The only confusion now, if I know exactly where's the output, is, okay, what kind of input do you have? Common mode or differential? Let's answer the question assuming differential. So AD is the gain when V in 1 is VID over 2 and V in 2 is minus VID over 2. When I have differential, purely differential, fully differential inputs, this will be at signal ground. All right, this will be a signal ground if the two inputs are fully differential. And the half circuit would be this, and it would be a common source amplifier with nothing between source and ground. So I know that here's VD1, VD1 over VI1 is minus GM1 R prime L, RD parallel RO1. But what is RD in this case? RD is actually RO3 parallel RO1. So that's VD1. And VI1 is VID over 2. So VD1 is minus 1/2 VID into this. VD2 is plus. It's the exact same thing. VO is VD2 minus VD1. And you take the difference between these two, you get VID into GM1 RO3 parallel RO1. In such circuits, we usually assume that GM1 is equal to GM2 and RO3 is equal to RO4. It's important for the circuit to be symmetrical. So AD is therefore VO over VID, GM1 RO3 parallel RO1. That's AD. ACM. Okay, let's squeeze ACM here. We don't need much space for ACM, and I will tell you why. Because I'm taking the output differentially, even if the current source here is not ideal, and it's not really ideal, but when I take the output differentially, if the two inputs are equal, this is non-ideal, and whatever I have here, I have perfect symmetry in the circuit. And if I have perfect symmetry in the circuit, it means that the voltage here would be equal to the voltage here, because everything else is equal. So when the two inputs are equal, the MOSFETs are matched, this is shared, VD1 is equal to VD2 by symmetry. It means VO is 0 and ACM is 0. Without doing much circuit analysis, just by using the symmetry in this case. Okay, I hope you're ready for the next slide. Here's the differential amplifier built out of cascodes. Okay, now we need some time to just understand what we have here. Okay, here are my inputs, VN1 and VN2. Where's the output? The output is not taken directly from the drains of M1 and M2. The output is taken here. So it's between the drains of M3 and M4. Okay, no problem. What do we have between the drains of M3 and M4 and the supply? I'm looking into the drain of M5 with a DC at its gate, and between the source of M5 and signal ground, I have another MOSFET with a DC at its gate, and the same thing here. So if I want to just look at this, here's the situation. I'm looking into the drain of this M5, and there's no signal at its gate. And between its source and ground, there is M7, and there's no signal at the gate of M7. So that's not, actually, this is something that we know. We've used this, and we know that there's a formula for this one. When you're looking into the drain of M5 and you have a situation like this, you would see RO5 plus RO7 plus GM5, RO5, RO7. So this is what we see here. This is the resistance that we see looking into the drain of M5 here. And this becomes like the RD that I had previously. So this is the RD now. So that's a large RD. This will be a large RD. Same, exactly the same as on this side. And again, M5 and M6 would be identical. M7 and M8 would be identical. A similar case we have here, where the current source is implemented using two MOSFETs. And we know why. Because when we do this, the output resistance of the current source becomes very large. So this is implementing a current source that is mirroring something that we're not showing. And its output resistance, RSS, would be RO9 plus RO10 plus GM9, RO9, RO10. In case we need it, we know what the output resistance is. Okay, so I have RD, and the current source. So that's starting to look like the circuit we had previously, except for M3 and M4. We did not have M3 and M4, but now we have them. So M3 and M4 are implementing a cascade amplifier. So now if I consider the half circuit for differential inputs, when this is VID over 2 and this is minus VID over 2, this will be signal ground when the two inputs are differential. So how does the half circuit look like? So differential inputs, half circuit would be something like this. RD, and RD is implemented by M5 and M7, and then M3 and M1, and then signal ground here. This is the virtual ground. So I have some DC voltage here, a DC voltage here. The input, the first input, and the output is taken here. And that's M1 and M3. So in this case, the half circuit is not a common source amplifier. If I did not have M3, it would have been a common source amplifier. If it's just M1 and RD, yeah, that's a simple common source amplifier. Now I have M3 in between. But that's something we've seen. This is the cascade. The cascade is exactly this structure, a common source followed by a common gate. And we've analyzed the cascade and we know what the gain would be if we cascade. So that's, again, we're familiar with this. We know what to do. All right, so what's the question? Oh, again, one of those confusing questions. What is the voltage gain? What kind of voltage gain? What is the voltage gain? Is it AD? Is it ACM? And where's the output? Do we know where's the output? Oh, here's the output. We know where the output is, but there's no plus and minus. Again, V out is between drains, but we don't know where's the plus, where's the minus. So I'll have to calculate AD when V out is plus minus like this. AD when V out is minus plus. ACM plus minus, and ACM minus plus. Now if I calculate this will be just minus of that. And if I calculate this will be the minus of that. So really, that's no big deal. So we can find AD from the half circuit. So AD from half circuit. So I'll use the cascode formulas. What about ACM? ACM, again, we're lucky that the out is taken between the two drains of M3 and M4, because this means that due to the perfect symmetry in the circuit, the voltage at the two drains would be equal when the two inputs are equal. So if I'm calculating ACM with the two inputs being equal, I have perfect symmetry, and the voltage at the drains of M3 and M4 would be equal, and I can just immediately say that ACM is 0. I don't need to calculate anything. AD is another story. AD, you would have to go back to the cascode formulas and calculate it, but it's just a couple of lines of equations, no big deal. So even with this circuit that kind of looks scary when we looked at it with 10 MOSFETs, it can be simplified to just common source or cascode or just formulas, structures that we've seen previously. And we can analyze it, find all kinds of gains, whether the inputs are differential or common mode, whether the output is minus, plus, plus, minus, differential, single-ended. We should be able to do that.